What would actually happen to a starship if we sent it into deep space? And check back 100 years later. At 1/10 the speed of light, it would have crossed light years, but its hull would be pitted by dust, its engines mostly useless, its electronics scarred by radiation, and its star maps partly wrong. In this video, we'll take that thought experiment seriously and break down system by system what a century in deep space would really do to a starship. At 0.1 C, your starship is moving at about 30,000 kilometers per second, around 19,000 miles per second. Keep that speed for a century and you cover roughly 3 light years. That is about 30 trillion kilometers, or 19 trillion miles. For comparison, Voyager 1, our fastest real probe, has spent almost 50 years just to reach about 24 billion kilometers, around 15 billion miles. You leave that distance behind in your first few months. By 100 years, the entire solar system is a tiny region behind you. The orbits of the planets, the Kuiper belt, even the far comets in the Oort cloud are all packed into a small patch of space you already passed long ago. You're no longer out near Pluto. You are between the stars, in the local neighbourhood of the Sun inside the Milky Way, so you are far, extremely far. But distance is not the only thing that changed. On the way out, you crossed a real physical boundary in space, one that no human has crossed in person. What invisible line did your ship punch through in less than a year? The Sun blows a constant stream of charged particles outward, the solar wind. That wind, plus the Sun's magnetic field, inflates a giant bubble around the solar system. That bubble is the heliosphere. At the edge of that bubble is the heliopause, where the outward push of the solar wind finally loses to the thin gas between the stars. Voyager 1 hit this boundary at about 120 times the distance from Earth to the Sun. At 0.1 C, your ship reaches that distance in under a year and keeps going. Inside the heliosphere, the Sun's magnetic field blocks some of the high-energy cosmic rays from the rest of the galaxy. Outside, that shield is gone. The intensity of galactic cosmic rays roughly doubles compared to near-Earth conditions. So after that first year, your starship is not in solar wind space anymore. It is sitting directly in the interstellar medium, the thin gas and magnetic fields that fill the galaxy. The plasma around you has different density, different temperature, different magnetic structure. Your hull, your electronics, and any crew now live in a harsher, more energetic radiation environment than anything near Earth. You change regions of space. But here's the next problem. You are not flying through a still background. The galaxy itself is moving, twisting and sliding while you fly. So what does your path even mean when everything around you is also in motion? The solar system orbits the centre of the Milky Way at about 220 kilometers per second, roughly 490,000 miles per hour. Nearby stars do not sit quietly, they drift with their own speeds, often tens of kilometers per second in different directions. The interstellar gas itself is not uniform. It flows, it has turbulence, it has small clouds and voids. Over 100 years, your course carries you through slightly different pockets of gas, with densities from around 1/100th of an atom per cubic centimetre up to around 1 atom per cubic centimetre. That still sounds like extreme vacuum, and it is, but at your speed, those atoms matter. They add up to a steady stream of particles hitting your bow, changing heating, charging, and drag in subtle ways. The local magnetic field also shifts as you move, which changes how charged particles and your own electric systems behave, so your straight line is not through a uniform emptiness. It is a path through a changing medium, with small but real differences in density and magnetism over decades. To know where you are and what forces are acting on you, you have to track not just your own engines, but the slow drift of the galactic environment around you. You try to do that by looking at the stars, but there's a catch. Over a human lifetime, the constellations you learned from Earth don't stay the same, so how do you navigate when even the sky itself has shifted since launch? Stars are not fixed points, they have proper motion, a slow sideways drift across the sky. Most move very slowly, but nearby stars can shift by several arc seconds per year. Barnard's star, one of the fastest, moves around 10 arcseconds per year. Over a century, that adds up to a clearly different position if you have precise instruments. Your ship uses star trackers, cameras that look at star patterns and match them to a stored catalogue. At launch, that catalogue was accurate. After 50, 80, 100 years, some patterns are stretched or warped. The angles between bright stars have changed just enough that if you keep using the old catalogue, your software starts to misidentify what it sees. At first, that error is tiny, maybe arcseconds. Then it grows to arc minutes, then more. That's enough to point an antenna slightly off Earth, or to aim a course correction burn in the wrong direction. Over light-year distances, a small pointing error turns into missing your target by millions of kilometers. So your Starship has to do something Earth's telescopes only rarely try over such long timescales. It has to rebuild its own map of the sky. It measures star positions again and again, calculates new distances using parallax, and updates its database, so the navigation system knows what the sky really looks like now, not what it looked like a century earlier. You have already lost the familiar shape of the constellations. You have replaced them with a dynamic, updated model that exists only inside the ship's computers. So you've changed your place, your environment, even your star map. There is one more twist. After 100 years of flying fast, your ship and Earth do not fully agree on how much time has passed. How old is your mission, if your own clock and Earth's clock disagree? At 1/10 the speed of light, special relativity slows time on the ship by a small amount compared to time on Earth. The factor here is about 0.5%. So if Earth measures 100 years since launch, the proper time on the ship is about 99.5 years. Nobody on board would feel this difference moment to moment, but it is baked into the physics. For daily life, 0.5% does not matter. For a mission that depends on extremely precise timing, it does. Communication windows are planned so that narrow radio beams hit a moving target decades away at the right moment. Navigation maneuvers may be timed so gravity from distant stars lines up in a certain way. If the ship assumes its own clock is the same as Earth's clock, those carefully calculated moments drift. So by the end of the 1st century, your Starship is in a place no human machine has ever been, outside the sun's protective bubble, in a changing galactic environment, under a sky that no longer matches the launch charts, running on clocks that have slipped out of sync with home. Just reaching this point has already stressed your navigation, your communications, and your planning. That raises the next question, and it is even more brutal. While all of this was happening outside, what has 100 years of vacuum, radiation, and dust actually done to the physical body of your ship, to the metals, plastics, and coatings that have been exposed to deep space since day one? Right after launch, every plastic, every paint, every glue on board is full of trapped gas, mostly water vapor, leftover solvents, plasticizers, all the stuff that makes a new car smell like a new car. In vacuum, those molecules start escaping. They seep out of panels, cables, circuit boards, and they drift into your air and out any vented surface. Early on, the outgassing rate can be around 1/1,000,000th of a kilogram per square meter per second. Then it drops, and keeps dropping by huge factors over the years. After a decade, it is already tiny. After a century, almost every molecule that is not really locked into the material is gone. Inside, the air stops changing. It reaches a kind of chemical truce with the metals and plastics. No more new fumes, no more slowest poisoning from leftover factory chemicals. The atmosphere becomes extremely dry, very stable, a little metallic in smell, but mostly just there. Outside, surfaces that once slowly fogged themselves with residue are now clean and inert. So in one sense, this is good. The ship becomes chemically quiet. But that calm hides the next problem, because once the gas is gone, the metals are naked, and naked metals in vacuum start doing something they were never supposed to do. If two very clean metal surfaces touch in hard vacuum, and there is no oil, no oxide layer, nothing in between, the atoms on each side can treat it like one continuous piece of metal. This is called cold welding. On Earth, air and moisture quickly build thin films on metal, so it rarely happens by accident. In space, those films can be stripped away. Over 100 years, any hinge, latch, rail or deployment mechanism that ever lets two bare metal faces rub together is a risk. Each tiny movement can scrape off whatever protective layer you had, until one day the parts just fuse, so your whole mechanical system is depending on micrometer thin coatings, lubricants only a few molecules thick, and special surface treatments that must survive decades of radiation, temperature swings, and that early outgassing storm. Miss one contact surface in design, forget to coat one pin or one sliding shoe, and 60 years in it seizes. That might be a backup antenna that never deploys, a radiator panel that refuses to swing out, or a hatch that will not open for an inspection robot. If cold welding quietly locks a key mechanism, you often do not get a second chance, but the metals are only half the story. Look around a real spacecraft, you see blankets, wires, tapes, insulation, flexible boots, transparent covers. All of that is polymer, plastic. So what happens to plastics that sit in deep space under radiation, cycling in temperature not for a few years but for 100? Space-rated polymers like Kapton, Teflon, and various epoxies are designed to handle harsh conditions, but their testing usually covers 15 to 30-year missions, not century cruises. The long chains that make them flexible slowly break under radiation, a process called chain scission. Every particle that flies through, every UV photon that hits, can snap a few molecular bonds. At the same time, some regions cross-link, making the material harder and more glass-like. The net effect, year after year, is simple. They get stiffer, more brittle, and weaker. Components that were once flexible, like cable jackets or insulation blankets, can reach a point where, at deep cold, below about minus 150 degrees Celsius, around minus 238 Fahrenheit, they no longer bend, they crack. A clamp tightened during construction might 70 years later dig into a now brittle wire coating and cut it open during a thermal cycle. A plastic boot that sealed a connector might crumble the first time a maintenance arm tries to move it after decades of sitting still. The ship is full of things that started off rubbery and slowly drift toward dry leaf. While the plastics are going brittle, the metals themselves are not fully stable either. Under constant load, even small loads, metals can slowly change shape over time, a process called creep. At high temperatures, this is fast. At cryogenic temperatures, it is very slow, but not zero, especially when you add in repeated thermal cycling between, say, 100 Kelvin and 300 Kelvin, that is from around minus 173 to plus 27 degrees Celsius, or minus 279 to about 80 Fahrenheit. Take a thin aluminum panel, 1 millimeter thick, held under mild tension, maybe as part of an antenna dish or an optical bench. Over decades, the internal grain structure in the metal can subtly rearrange, dislocations move, little defects migrate. The total change in length might be only a few micrometers, but in a high-precision instrument, that is enough to move a focal point, to slightly warp a reflector, to throw a beam pattern off. In big structural trusses, this kind of drift might not break anything, but in tightly tuned components, it shifts performance. The ship you end up with after 100 years does not have exactly the same alignments and tolerances it launched with, even if nothing ever snaps in a dramatic way. And all this is happening in what most people call empty space. No air, no rain, no salt water, so no corrosion, right? Not quite. The way materials age in deep space is different, but chemistry never really stops. Early on, outgassed water and organic vapors from inside the ship can condense on cold exterior surfaces. Those thin films, hit by hard ultraviolet light and charged particles, slowly break apart and react with the underlying material. Even far from Earth, trace oxygen inside alloys or trapped in coatings can work its way to the surface and form oxides. Over many years, thin metal films can darken, turn rough, or start to flake. Paints and specialized thermal control coatings designed with precise reflectivity and emissivity, gradually change their properties. That might not sound dramatic, but your thermal control system depends on those numbers. If a radiator panel that was supposed to radiate heat very efficiently loses that ability by 10 or 20%, internal equipment has to run hotter or run less often. If a previously bright reflective surface on the sun-facing side slowly darkens, it absorbs more energy, driving temperatures up. The ship's overall temperature balance, the careful heat budget set on the ground, drifts over decades just because surface is quietly aged in a way nobody has ever watched for a full century. So after 100 years, the hull of your starship is not just fine. It is chemically dried out, its metals are at risk of cold-welded joints, its plastics are stiffer and more fragile, its precision structures have crept and shifted, and its coatings have changed their thermal behaviour. From a distance, it still looks like the same ship. Up close, it is a different material object than the one that left Earth. And that leads straight into the next threat, because all of this slow aging is happening while the hull is being peppered by high-speed dust and micrometeoroids, tiny projectiles that hit so hard a grain smaller than a grain of sand can punch holes in metal. So how does a century of constant impacts reshape the skin of your starship? Space between planets and stars is not perfectly clean. For micron-sized grains, interplanetary space sees something like a few hits per square metre per year, sometimes more, sometimes less. Interstellar space is less well measured, but it is not zero. Now scale that up. Your hull is not a small satellite. It might easily have 1,000 square metres of exposed area, about the footprint of a small office building. Spread that across a full century and you are talking about millions, maybe billions, of tiny particles smacking into your ship. Each one is tiny, sub-millimetre, often far below what a human eye could see. But the key is not their size, it is the see it. Even in quiet regions, you're getting a constant drizzle of high-velocity dust. There is no pause button. The Starship experiences this 24 hours a day for 100 straight years. There is no atmosphere to slow anything down. Everything that is on a collision course hits at full speed. And that leads to the next step, which is where this starts to sound less like gentle dust and more like weapons testing. At your cruise speed, how much damage does one of those tiny grains actually do? At 0.1 C, around 30,000 kilometers per second, a dust grain does not behave like dust anymore. Even a 1 micrometer particle, smaller than typical bacteria, carries enough kinetic energy at those speeds to be compared to a rifle bullet in terms of impact effect on a small area. If you go up just a bit in mass, to around 1 milligram, about a grain of fine sand, the energy jumps into the hundreds of millions of joules. That is roughly like detonating 100 kilograms of TNT, concentrated into a spot the size of a pinhead. Most particles you hit will be much smaller than that, but even at more normal relative speeds, tens of kilometers per second, not a tenth of light speed, a micron-sized grain can punch through thin aluminum and turn a small volume of metal into plasma and vapor. The outer hull over time gets packed with micro craters. Some are only a few micrometers across, some reach millimeter scales, but together they change a smooth panel into something more like a pitted sponge. You do not see this from far away. The ship still looks sleek from a distance. But if you ran your hand over the armour with a good glove, you would feel the texture, the scars of millions of hits. And that's assuming none of those impacts hit something critical directly. So the obvious question is, if dust is this violent, how do you keep your real pressure hull and sensitive systems from getting shredded? The answer is, you do not expose them directly. You wrap the real hull in sacrificial layers that exist only to get destroyed. Modern spacecraft already do this using Whipple shields, and your Century ship scales that idea up. Instead of one wall, you have multiple thin bumpers in front of your main structure, spaced a few centimeters, maybe tens of centimeters, away from it. When a high-speed grain hits the first layer, that thin skin is designed to break and vaporize. The incoming dust and a bit of the shield turn into a hot plasma cloud, spread out over a wider area. That cloud then hits the second layer as a broad splash, not as a tiny concentrated bullet. The second layer absorbs the energy over more surface, and by the time anything reaches the real pressure hull, the impact is much less likely to punch through. Over 100 years, those outer sacrificial plates take a beating. They end up looking like they were hit by shotgun blasts from every direction, over and over. Holes, pits, torn edges, discoloured patches, all of that shows up on the first layers. You design them to be simple, cheap, and structurally non-critical. If a plate breaks off, the ship survives. If it looks ugly, nobody cares. Its job is to die so the rest of the ship does not. But even with all that, you might ask, how much metal do you actually lose to this process? Purely from erosion, not from single catastrophic hits. Does the ship literally get thinner as the years go by? When scientists estimate micrometeoroid erosion in interplanetary space, they get numbers on the order of 1/10 of a millimetre to 1 millimetre of material lost per million years for something like exposed aluminum. 100 years is just 1/10,000th of a million years. That means you're talking about losing micrometers of thickness over a century, not centimetres. Your armour does not vanish. The bulk of the hull is still there. The real risk is not uniform thinning, it is randomness. A radiator panel could be doing fine overall except one unlucky hit punches a pinhole leak right where coolant lines run. A cable bundle could function perfectly for 80 years, then a micro crater cuts through a few key conductors. A fuel line wall might lose just enough local strength from a series of hits, plus thermal cycling to crack open. You're not fighting sandpaper, you're playing a century-long game of roulette, where every square centimetre of exposed system is a potential failure point. And then there is an effect that is less obvious, but just as serious. Every time one of those grains hits and makes that little plasma cloud, it does not only damage the metal, it also hits your electrical system in a way that is much harder to see and predict. So what is that doing to your electronics over decades? A hypervelocity impact vaporizes both the grain and a tiny bit of the hull around the impact point. The result is a small hot blob of ionized gas, a plasma, that expands quickly away from the surface. That plasma cloud carries charge, and it is moving through the electric and magnetic fields around your ship. Any nearby wires, boards, or metal structures can have voltage spikes induced in them when that cloud rushes by. Each spike might only be tens or hundreds of volts, but it is fast and sharp. Over the course of decades, with millions of micro-impacts, your electronics experience thousands of these pulses. Good design uses solid grounding, proper shielding, surge suppressors, and robust power conditioning to absorb them. But nothing is perfect. Some pulses will get through. They can flip bits in memory, stress insulation, and accelerate the aging of components. So your power system and data system are not only dealing with cosmic rays and normal wear, they're also living in a constant storm of tiny electromagnetic kicks caused by dust hits on the hull. It is not enough to design for a 3-year mission with a few dozen major impact events. You must design for 100 years and thousands of events, each one a chance to nudge your electronics closer to failure. By the end of the first century, your Starship's skin tells a very clear story. The outer shields are torn up and cratered, the underlying hull is pitted, some vulnerable lines and panels have scars or patches from impacts, and the electrical system has survived wave after wave of random spikes. The ship is still there, still flying, but it has been physically hammered the entire way, and that's just from solid dust and tiny rocks. On top of all those visible scars, there is another threat that never turns off, never leaves a crater you can see, and quietly attacks every material and every chip from the inside out, the constant radiation of deep space. So what has 100 years of that invisible bombardment done to your ship? Once you leave Earth's magnetic field, the background radiation level jumps. Astronauts near Earth see around 0.5 to 1 millisievert per day. Out in interstellar space without the heliosphere to help, that background can go higher. Stretch that over 100 years and an unshielded surface on your hull can see well over 10 sieverts total dose, maybe much more. Easily enough to kill a human many times over if they sat there with no protection. For materials, it works differently, but it is still bad news. Each high-energy proton or heavy ion slams into atoms in whatever it passes through, knocks them out of their normal positions, and leaves behind a trail of damaged crystal lattice. This is called displacement damage. One particle is nothing, but over decades the total number builds into billions and trillions. Microscopic defects join into clusters. They change how metals bend, how semiconductors conduct, how plastics hold charge. Radiation becomes a slow vandal, never taking a big bite, just tapping away at the atomic structure of everything all the time. To protect a human crew, you need real shielding, meters of water, polyethylene, or other hydrogen-rich material around main living areas. For electronics, you might bury sensitive units deep inside the ship, behind fuel tanks, cargo, and structural mass. But you cannot hide every cable, every sensor, every camera, every panel. Parts of the ship will always be in the open, taking the full cosmic ray hit for the entire 100 years. If radiation can move atoms around in solid metal, what does it do to devices built from layers only a few dozen atoms thick? Your electronics. Spacecraft already see single-event upsets, SES, where one energetic particle flies through a memory chip and flips a bit from 0 to 1, or the other way around. On a short mission, you handle this with error-correcting codes and regular scrubbing, reading the memory, fixing errors, and writing the corrected values back. You also duplicate critical processors, sometimes triplicate them, and vote on their outputs so one bad flip does not crash the system. On a Sentry mission, the total number of these bit flips is huge. Every day, some fraction of your memory experiences hits. Multiply that by 36,500 days and you're dealing with millions of upsets over the life of the ship. You can't prevent them, so your entire computing architecture is built around catching them, correcting them, and routing around the damage, and that is just the temporary effects. Radiation also adds permanent damage in semiconductor devices. Charge builds up in oxide layers. Threshold voltages drift. Some transistors slowly change behavior, needing more or less voltage to switch or leaking more current when they're supposed to be off. At some point, sections of a chip develop stuck bits that never change, no matter what you tell them to do. Even radiation-hardened parts with thicker layers and special designs are not immune. They just last longer before weakness shows up. So your Starship's computers are not just running code, they're running a constant survival routine, checking and rechecking their own memory, moving critical functions to healthier hardware, and slowly downgrading as parts of the system age out. The software stack must expect hardware to fail not once but continuously over 100 years. You can ground metal structures and harden chips, but what about the materials in between? The plastic and epoxy that are supposed to insulate everything electrically? Those do not just sit there safely either. The polymers used as cable insulation, circuit board substrates, and connector housings can trap charge when radiation passes through them. Each high-energy particle leaves behind tiny pockets of charge inside the material. Over years, these pockets build up into internal electric fields. If the field gets strong enough in a local spot, it can cause a tiny breakdown, a miniature spark path called an electrical tree. That path can carbonize, turning from an insulator into a weak conductor. This usually does not cause a dramatic failure on day one. Instead, you get slowly increasing leakage currents, extra noise in signals, and weird intermittent faults that come and go with temperature changes or voltage levels. After a few decades, some cables that started as perfect insulators are now slightly conductive in spots. In 100 years, a poorly shielded run or a board living in a harsh radiation hotspot may have gone through multiple partial breakdowns. The design has to account for that, with derated voltages, extra shielding where it matters, and the expectation that some paths will become unreliable and must be backed up. Radiation does not just attack electronics and insulators, it also alters how your ship sees. Any system that depends on transparent materials is slowly losing clarity. Glass and certain crystals darken when exposed to radiation. This happens on the International Space Station, it happens in nuclear reactors, and it will happen on your Starship windows, lenses, and fiber optics. High-energy particles create color centers, defects in the glass that absorb specific wavelengths of light. Over years, transmission slowly drops. A lens that started out passing 99% of incoming light at a given colour might fall to 90%, then 80%, or worse, in that band after decades of exposure. For your star trackers, telescopes and navigation cameras, that means their signal gets weaker even if the stars stay just as bright. Noise in the detectors and electronics stays the same or even grows, so the signal-to-noise ratio drops. To compensate, the optics have to be oversized at launch, collecting more light than you strictly need at first, so that even with radiation darkening they still have enough margin later on. Some systems might use protective covers that only open during observations to reduce total dose. Others may rely on redundant optical paths and regular calibration, constantly measuring how much sensitivity they have lost and adjusting exposure times. Finally, underneath all of that, there is the bulk metal, the skeleton of the ship. In nuclear reactors on Earth, we know that high-energy particles can harden and embrittle metals. In interstellar space, the flux is lower, but the timescale is long, so what happens to the bones of the Starship after taking particle hits for a century? Most of the damaging particles out there are high-energy protons and heavier ions, not the intense, fast neutrons you get in a reactor core, but they can still displace atoms in metal. Those displacements create clusters of defects, little regions where the crystal's messed up. Over time, that can make some alloys harder, less able to deform smoothly, and more likely to crack without warning instead of bending. This is called embrittlement. For thick, heavily loaded structural beams with big safety margins, the effect over 100 years in deep space might be small. But for thin components, lightly loaded brackets, springs, fasteners, or any piece that already runs closer to its limits, radiation-induced embrittlement adds to all the other aging processes like thermal fatigue and micrometeoroid damage. A part that would have survived normal fatigue on its own might crack early because radiation made it less forgiving. That is why designers of a true century ship avoid alloys that are known to be radiation sensitive, and they model not just initial strength but the total particle dose, the fluence each piece will see over the mission. They build in extra margin not just for launch loads, but for the unknowns of living in that invisible particle storm for 100 years. So by the time you hit the 100-year mark, radiation has done what dust and impacts alone could not. It has quietly altered metals at the atomic level, chipped away at electronics, weakened insulators, and dimmed your eyes on the universe. The ship is still flying, but it is not the same machine that launched, even if every bolt is still technically in place. Now add one more stress on top of all that. In deep space, there is no air to soften temperature swings. Your ship heats and cools only by radiation, and that means brutal thermal extremes cycling over and over for a century. How much damage does that do when you stack it on top of everything irradiation has already started? In deep space, there is nowhere to smooth anything out. Your ship heats and cools only by radiation, and that is brutal over a century. If one side of the hull has a view of a distant star, it soaks up that light and warms up. The opposite side looks out into deep space at about 3 Kelvin, around minus 270 degrees Celsius, about minus 454 Fahrenheit. Without smart thermal design, just rotating the ship or changing attitude for a communication pass can swing some parts from around plus 100 degrees Celsius, about 212 Fahrenheit, down to minus 150 degrees Celsius, about minus 238 degrees Fahrenheit. That is a swing of 250 degrees or more, back and forth, again and again. You might do that every orbit around a star, every few hours, or whenever you switch pointing modes. Over 100 years, you repeat those cycles millions of times. There is no breeze to slowly cool or gently warm surfaces. They radiate heat away directly to space, and their temperature jumps when sunlight hits or disappears. Every one of those swings makes the structure breathe. Metals expand when they heat up and shrink when they cool down. Take a 10-meter aluminum beam, about 33 feet long. For a 100 degree Celsius swing, It changes length by around 1/4 of a millimetre, roughly the thickness of a couple of sheets of paper. One cycle is nothing. 1,000 cycles is still fine, but millions of cycles over a century start to matter. Cracks do not show up in the middle of a perfect bar first. They show up where you drilled a hole, cut a notch, welded a joint. These spots are stress concentrators, local weak points. Every time the beam expands and contracts, stress piles up around those points. At first, you just grow microscopic cracks, too small to see even with a microscope. Later, those cracks join, they get longer, and then one day, the piece fails. On Earth, fatigue tests rarely cover 100-year cycles under space-like conditions. Engineers test for thousands or maybe millions of cycles, but they still have to extrapolate to a full century of on-off heating in vacuum. So they add safety factors, beef up beams, round off sharp corners, and try to avoid learning the hard way that a key truss behaves like a paperclip bent one too many times, except the last bend is just another normal temperature change. The places that suffer most are often the same places that have to dump heat for the entire ship, the radiators. These are not thick armoured slabs, they are big thin panels, designed to spread heat from electronics, life support or reactors out into space. Radiators rely on coatings with high emissivity, surfaces that are very good at throwing heat away as infrared light. At launch, those coatings are tuned very precisely, but after years of micrometeoroid hits, radiation darkening and chemical changes in the paint or surface treatment, that emissivity can shift. Lose 10% performance and suddenly you have to run your internal equipment a bit cooler. Or you accept that everything runs a few degrees hotter than planned. Or you start taking turns, shutting down non-critical, or so that critical ones can stay in a safe temperature range. On top of that, every radiator panel is being peppered with micro craters, each one a potential start of a crack or a leak path for coolant inside. The panels flex slightly with every temperature cycle, so those tiny flaws get stressed over and over. After 100 years, your radiators are not pristine, high-tech panels anymore. They are patched, scarred, and operating with less margin than the designers had on day one. Now think about all the parts that have to move, but only once in a long while. Things like backup antenna gimbals, telescope doors, deployment booms. They sit in the cold and dark for decades. What do those temperature extremes do to the lubricants that are supposed to keep them moving? Spacecraft use special lubricants, like perfluoropolyether oils or solid lubricants such as molybdenum disulfide. These are picked because they work in vacuum and can handle high and low temperatures better than normal oils and greases, but even they have limits. At cryogenic temperatures, below roughly -150 Celsius, about -238 Fahrenheit, many fluids become glass-like, extremely thick, barely able to flow, some go fully brittle. If you then ask a motor to turn a bearing that has been sitting in that state for 40 or 70 years, you may find that the lubricant behaves more like glue than oil. The motor stalls, the bearing skids instead of rolling, and you damage the surfaces. For a mechanism that only needs to move a few times in the entire mission, you cannot count on a traditional wet lubricant sitting there, perfect for a full century. So critical long sleep systems either get heaters, warming them up for hours or days before actuation, or they are designed around dry, solid lubrication, with materials that slide on each other without oil and can tolerate a century of neglect. In some cases, you just accept that anything that has not moved in decades is probably dead, and you design the mission so you do not depend on a one-time deployment late in life. Underlying all of this is the idea that the ship's thermal behaviour at launch will stay about the same, but it doesn't. As surfaces darken, flake and get cratered, the balance between how much heat you absorb and how much you emit drifts. Thermal engineers start with careful numbers, how reflective a panel is in visible light, how emissive it is in infrared. They use those to set up a stable average temperature, so the ship does not freeze or overheat. But after 20, 50, 100 years of radiation damage, micrometeoroids and chemical changes, those optical properties can shift a lot. A panel that once only absorbed 20% of incoming light might now be taking in 30 or 40%. That extra absorbed energy can raise local temperatures by tens of degrees, enough to push electronics or batteries out of their safe range. So temperature control stops being a simple design problem you solve before launch and never touch again. It becomes a dynamic control challenge. The ship has to monitor its own temperatures, compare them to expected values, and adjust. It might rotate a little differently, change which surfaces face starlight, throttle back certain instruments during hot phases, or run heaters in new ways during cold phases. The longer the mission goes, the more active that management has to be, because the basic thermal personality of the ship is drifting away from the ideal that was drawn on Earth. By the 100-year mark, your Starship has gone through millions of thermal cycles. Its beams have flexed and relaxed endlessly. Its radiators have lost some performance, some lubricants have frozen and cracked, and the neat thermal balance it launched with has shifted. You can keep it alive by constantly adjusting, but there's room for errors shrinking. Now add one more layer of stress, your propulsion systems and attitude controls, the very things that let you steer and correct for problems, are also sitting in this frozen and fried environment for a century. Fuels decay, thrusters erode, wheels wear out. So after 100 years of heat and cold, what is actually left of your engines and your ability to point the ship? Start with the most familiar stuff, chemical propellant, things like liquid hydrogen, liquid oxygen, hydrazine. These are great for launch and short missions, but they are terrible at just waiting for a century. Liquid hydrogen boils away even with excellent insulation. To keep it liquid for more than a few years, you need active cryocoolers running all the time, and almost perfect tanks. That means you are spending precious electrical power just to stop your fuel from quietly leaving through the vent. Over 100 years, unless you've burned it early or run those coolers continuously with high reliability, your liquid hydrogen is gone. Liquid oxygen is easier to store, but not by much at these timescales. It also wants to boil off if the tanks ever warm up. Even storable propellants like hydrazine and nitrogen tetroxide, which can sit at room temperature, do not last forever. They slowly break down, forming gas bubbles and solid sludge. That sludge can clog filters, valves, and injector ports. By the time you hit the 50 or 80 year mark, a tank that still shows full might hide propellant that no longer flows cleanly through tight plumbing. So a true Century-class mission with chemical propulsion has one realistic strategy. You use almost all of your big chemical burns early, to leave the system and shape your trajectory, then you shut those systems down. You do not count on firing a large chemical stage in year 70. At best, you might keep a small amount of hypergolic or coal gas propellant alive for fine control in very robust tanks, but even that gets harder the longer you stretch the timeline. That is why long-range missions lean on electric propulsion, ion and plasma thrusters to squeeze enormous efficiency out of a small mass of propellant. But those thrusters have their own long-term failure modes. So what does a 100-year mission do to an ion engine? Ion engines and Hall thrusters work by accelerating ions through electric fields, or along channels, to very high speeds. The ions slam into grids or channel walls and slowly erode them. Erosion rates are measured in micrometers per 1,000 hours of operation. That sounds tiny, but if a thruster runs for 10,000 hours total, which is only a bit more than a year of continuous firing, you can lose tenths of a millimeter from critical parts. On a 100-year mission, you probably don't run thrusters all the time, but you might have long campaigns early on, and a handful of course correction campaigns later. Over that life, grids and channels collect erosion, plus contamination from outgassing and dust. The precise shapes of those parts, which control the ion beam's angle and focus, get distorted. That reduces efficiency, increases stray ion hits on the spacecraft, and at some point can even punch through grids entirely. So a realistic Starship design does most of its major electric propulsion work early in the trip. It accelerates for months or years, reaches cruise, and then shuts most engines down forever. Maybe you keep a few small thrusters in reserve, accepting that by year 80 they are worn and only partly effective. Your Sentry ship is not a fighter jet with engines ready to throttle up at any moment. It is closer to a thrown spear, most of its velocity locked in long ago. To keep any of this running, you need power, and for that, long missions usually turn to nuclear options. But even nuclear systems have lifetimes, so what does 100 years do to nuclear power and nuclear propulsion hardware? Radioisotope power systems like RTGs using plutonium-238 start strong and then slowly fade. Pu-238 has a half-life of about 88 years, and on top of that the thermoelectric converters that turn heat into electricity degrade over time. You lose close to 1% of power per year overall. After a century, you can easily be down to less than half of your original output, often closer to a third once converter decay is included. If you carry a fission reactor or a nuclear thermal engine, you probably do not run it for 100 years straight. You fire it for a relatively short main burn, maybe a few burns, then shut it down to coast. But even when a reactor is off, the fuel still produces decay heat and radiation. Nearby materials continue to be exposed, getting embrittled and activated. Coolant systems, control rods and pumps sit still, aging. Restarting a nuclear propulsion system after 60 or 80 years of dormancy is extremely risky. Valves could be stuck, sensors dead, control electronics degraded, and the structural supports around the core weakened by radiation and thermal cycling. Very few mission designers would bet the entire mission on "we'll light the nukes again in year 75. So just like chemical and electric systems, nuclear propulsion is mostly a front-loaded tool. Use it early, then treat it as spent hardware that you keep cooled and contained, not as an engine you rely on in your final decades. For fine control and pointing, you do not want to use big engines anyway. You lean on attitude control systems, reaction wheels, control moment gyros, small thrusters. But those two are slowly eaten by time. Reaction wheels are basically flywheels on bearings. Spin them up, the ship turns the other way. Over time, bearings wear, lubricants age, and internal friction rises. Some space-grade wheels are tested for the equivalent of 10 to 20 years of life. A 100-year mission blows past that. If you depended on one set of wheels, you'd be in trouble. So a Sentry ship attitude system probably uses multiple redundant wheel sets, with magnetic bearings where possible to reduce wear, and extremely conservative duty cycles. You keep wheels spinning gently instead of slamming them from stop to stop. You offload accumulated momentum using small thrusters, likely cold gas or very simple electric thrusters that do not depend on exotic, unstable chemicals. You accept that some wheels will fail along the way, and you design so that losing a few does not mean losing control. Even so, you still depend on leftover propellant or gas bottles for desaturation burns. That means those tanks and valves have to work after sitting for decades. They are smaller and simpler than a main engine, so the odds are better, but it is still another piece of equipment you're asking to wake up after a very long sleep. All of this is for fairly standard propulsion and control. But many interstellar concepts lean on exotic drives like light sails or magnetic sails, which need almost no onboard propellant. On paper, that looks perfect for Sentry missions. In reality, it opens a new set of aging problems. A light sail pushed by photons from a star or lasers has to be huge, often kilometers across, made of extremely thin reflective material. Over 100 years, micrometeoroids and dust punch an enormous number of holes in it. The sail slowly turns from a smooth mirror into something like lace. Each hole slightly reduces effective area and can change how the sail deforms under pressure. Tears can spread along stress lines, changing its shape and making control harder. A magnetic sail or mag sail uses large superconducting loops to create a magnetic field that pushes against the charged particles in the interstellar medium. Those coils have to stay cold, intact, and powered for decades. Their supports see the same radiation and thermal cycling as the rest of the ship. Insulation can break down, quench events can damage conductors, and slow mechanical creep can change coil geometry, altering the field. So exotic drives reduce propellant problems, but they dramatically increase exposed surface area and structural complexity. You trade away tanks that boil off and rot for sails that get shredded and coils that degrade. Over a 100-year run, no propulsion option is easy. You're just choosing a different way for physics to attack you. By the time your Starship has been flying for a century, the truth is blunt. Most major propulsion systems have already done their job and are either shut down or operating with reduced capability. You're mostly relying on whatever attitude control hardware you manage to keep alive, and whatever small thrusters still fire cleanly. The ship is still moving fast, but almost all of that speed is a relic of decisions made generations ago near the start. And that raises the next uncomfortable point. If your ability to maneuver and fix problems from the outside is fading, then your survival depends more and more on what is happening inside the wires and computers in the nervous system of the ship. So after 100 years of radiation, dust and thermal stress, what shape is the electronics and software that control everything actually in? On the ship, you are not using cutting-edge gaming GPS or server CPS. You are using radiation-hardened processors, usually running at tens to maybe a few hundred megahertz, not gigahertz. They have wide safety margins, thick insulating layers, and simple conservative designs. They are chosen because they survive radiation and temperature swings, not because they are fast. Back on Earth, whole computing paradigms can change in a century, from classical chips to neuromorphic hardware to quantum systems to things we cannot predict. Your ship does not get those upgrades. It is stuck with what it launched with, plus whatever reconfigurable hardware you built in from the start, like FPGAs or custom programmable accelerators. So the only way your Starship keeps up with new ideas is through software and reconfiguration. The hardware is slow, but the architecture has to be flexible. You design the system so you can rewire logic internally, change what cores do what, and repurpose spare units as others fail. The ship's computing stack is not a fixed product. It is a toolkit that can reshape itself over time as long as the underlying silicon is still alive. That brings up a deeper problem. The hardware can survive, but the data on it cannot unless you fight for it. Over 100 years, stored bits do not just sit there politely, they drift, flip and decay. So what happens to your code and records when every bit is under attack from physics? Cosmic rays can flip individual bits in RAM. Flash memory cells slowly leak their stored charge. Magnetic storage, if you use it at all, sees domains drift. If you just write data once and walk away, in a decade or two, that data is no longer guaranteed to be correct. Over a century, it is junk. To stop that, the ship has to run constant maintenance. It uses error-correcting codes, so each block of data carries extra parity information. It periodically reads every block, checks for errors, fixes any flipped bits it can correct, and writes the clean version back. This process, called scrubbing, never stops. Day after day, decade after decade, the ship is quietly scanning and repairing its own memory. But here is the catch. Over 100 years, you are doing billions of these corrections. Most are fine, some are not. Sometimes 2 or more bits flip in the same block before the next scrub, and your ECC scheme cannot fully repair it. Sometimes a sector goes bad physically and starts throwing more errors than the algorithms were designed for. If you are lucky, the system spots that and marks the block as bad, moves the data to a different area and updates its tables. If you are unlucky, subtle, uncorrected errors sneak into rarely used code paths, or into old configuration files, or into archived navigation data that you one day need again. That is bit rot in a deep sense, data that looks like it is still there, but is now slightly wrong. The entire software design of a Century ship has to assume that stored information is slowly drifting toward noise, and it has to actively push back forever. Even if you keep the bits clean, there is another slow threat: software complexity itself. The longer a system runs, the more rare edge cases it encounters, and the more hardware pieces fail in strange partial ways. How does your ship's software not collapse under its own weight in year 60 or year 90? On a short mission, you can ship frozen firmware, a set of programs tested against a fixed hardware configuration. with a known set of sensors and actuators. On a 100-year mission, almost nothing stays fixed. Sensors start reading noisy, then fail. Thrusters lose performance. Memory chips develop bad regions. Timers drift. Networks between modules develop intermittent faults. The control software has to behave less like a static program and more like an immune system. It watches for unusual patterns, flags modules that start behaving out of spec, and quarantines or restarts them. It can rewrite its own code or load updated versions of algorithms to handle new conditions. It can reroute commands around damaged network segments and reassign tasks when a processing unit starts to show too many correctable errors. In practice, that means the onboard AI or control stack keeps evolving. The system you are running in year 90 is not exactly the system you launched with. It has patches, workarounds, removed features, new diagnostics, and emergency modes that only exist because some part failed in year 46, and the ship had to invent a way to stay functional. This is powerful, but it comes with risk. Over time, the software can become tangled hard even for its own maintenance routines to fully understand. Low all that logic, there is still basic hardware, solder joints, connectors, traces, all the physical stuff that lets electrons move, and that physical layer is also acting mechanically for the entire journey. Solder joints expand and contract with every thermal cycle, just like beams and panels. Tiny cracks can form at the edges of chips, especially at the corners and on large packages. On Earth, in harsh environments, we see electronics fail in years to decades from this alone. A Sentry ship deals with far more cycles. To reduce the risk, you underfill chips with epoxy, you avoid big heavy components hanging off boards, and you prefer welded or bonded connections instead of loose plug-in connectors. Still, some percentage of joints will develop micro cracks over 100 years. Some connectors will slowly loosen, especially ones that ever moved. Some traces will be damaged by micro arcs or dust impact-induced spikes. You cannot guarantee a perfect board forever, so the network between computers, sensors and actuators has to be redundant, with multiple paths and spare lines. Routing logic must detect when one path starts dropping packets or showing errors, and automatically switch to healthier routes. The idea that this one cable always carries this one critical signal is a bad idea on a Sentry ship. Underneath all of this is something that seems simple but turns into a deep problem over a long mission: timekeeping. Every subsystem has its own clock, none of them are perfect. They all drift just a tiny bit. But over 100 years, tiny drift becomes big disagreement. A clock with a drift of just 1 part per million will be off by about half a minute per year. Over a century, that is close to an hour. If two subsystems do not resynchronize, their views of now can separate by minutes or hours. For tasks like logging, that is annoying. For control loops, where one system expects a reaction in milliseconds and the other thinks it has seconds, that can cause unstable behavior, weird oscillations, and hard to debug faults. To keep a unified time, the ship needs regular sync routines. It can use internal master clocks, cross-checked between units. It can also reference external very stable signals, like pulsars or distant quasars, to correct drift. But if those routines fail, or if some subsystem gets isolated behind failing links, its internal timeline can go rogue. Then, even if its hardware is fine and its software is uncorrupted, it may act late or early relative to the rest of the ship, creating bugs that never showed up in a 5-year ground simulation. By the end of 100 years, your starship's brain is a patched, self-healing but heavily scarred system. Its processors are old and slow, its memories are full of battle marks from radiation, its software has grown and shed layers like a living thing, and its internal sense of time is something it has to constantly fight to keep coherent. The ship is still thinking, but it is thinking with hardware and code that have been under attack since the day it left. And that leads to the most human question of all. If the electronics and software that run the ship are this fragile over a century, what happens if you put actual human bodies and minds inside that environment and ask them and their children and their grandchildren to live there for 100 years straight? Putting hardware through 100 years of deep space is brutal, but putting human bodies and minds through it is on another level. So the first question is simple. Could you even survive the radiation dose if you tried to just ride along unprotected for a century? Unshielded in deep space, an astronaut can see around 0.5 to 1 millisievert of radiation per day. Over a year, that's roughly 0.2 to 0.4 sievert. That's already close to or above some space agency career limits for a single mission. Stretch that to 100 years and you're talking tens of sieverts, easily enough to guarantee lethal damage multiple times over. So a real sentry ship with people on board cannot rely on thin metal walls. You need meters of shielding around living areas. Water is great, polyethylene is great, and regolith or other hydrogen-rich material also works well. You're basically burying your crew inside a big moving bunker, using fuel, water tanks, cargo, and dedicated shielding blocks to cut radiation by orders of magnitude. Even then, the dose will not be zero. High-energy cosmic rays are hard to stop completely. Some fraction still gets through and hits tissue. Over decades, even a modest rate adds up. That means higher lifetime cancer risk for everyone. Tissues that divide quickly, like bone marrow, are especially vulnerable. You worry about blood cancers and long-term DNA damage that normal Earth lifespans would never have had to carry. You can monitor dose, move people around to lower their exposure, and design safe storm shelters for the worst events. But you cannot make deep space biologically harmless. You're managing the damage, not eliminating it. Then add gravity, or rather, the lack of it. We already know what months in microgravity do to the human body. Bones get weaker, muscles shrink, fluid shifts mess with vision and the heart. On the ISS, without strict exercise, astronauts can lose 1 to 2% of their bone mass per month. Now extend that out, not for half a year, but for an entire life. For a 100-year mission, living full-time in microgravity is not an option. You need artificial gravity, something that gives your body a steady pull similar to Earth's 1G. The most realistic way to do that is a rotating habitat. If you build a ring about 100 meters across, spinning it at around 1 revolution per minute, the centrifugal effect at the rim can feel like 1G downward. Floors feel like floors again. Down is toward the outside of the ring, and people can walk, run and lift in something close to normal conditions. But that only works if you keep the system very stable. If the spin rate drifts, if the ring wobbles, if large masses move around without careful balancing, you get weird, changing gravity fields that mess with the inner ear, the cardiovascular system, and skeletal loading. Over decades, any persistent mismatch between what your senses feel and what your body expects can cause long-term issues. A sentry ship with humans is basically a giant medical experiment in rotational habitats, and any mistake plays out across generations. On top of the crew themselves, the ship is also home to something many people forget: microbes. Your bacteria, your fungi, your entire microbiome does not stay frozen for 100 years. It evolves. Humans carry trillions of microbes on and inside their bodies. Every surface you touch, every air duct, every waterline collects and breeds its own communities. We already see this on the ISS, where certain strains become very good at surviving in closed, metal, microgravity environments. Now give those microbes 100 years, strong disinfectants, constant radiation, recycled air, and very stable temperatures. You create a powerful selection pressure. Strains that can handle dry air, cleaning chemicals, and low nutrients survive. Others die out. Some organisms will learn to sit in tiny cracks and biofilms, forming stubborn colonies on filters, behind panels, or inside condensation traps. Some may become more resistant to antibiotics you use. Over time, the microbial ecosystem of the ship drifts away from Earth norms. Keeping pathogens under control becomes a constant active process. You'll be sequencing microbes, tracking which species are rising or falling, updating cleaning protocols, and probably changing which disinfectants you use as certain ones lose effectiveness. The ship is not just a machine, it is an evolving ecosystem, and you're playing a never-ending game to keep that ecosystem from turning against its human hosts. Then there's the long-term biological story, genetics and generations. On a multi-generation mission, some people are born on the ship, grow up, have children and die without ever seeing a planet. What does that do, not just to their bodies, but to the population as a whole over 100 years? Radiation, even when reduced by shielding, still leaves a low background of DNA damage and mutations. Diet is different, based on closed-loop agriculture and stored nutrients. Gravity, even with a rotating habitat, might be slightly different from Earth's, or interrupted during repairs and emergencies. All of that shapes how genes are expressed, how tall people grow, how their immune systems develop, how their bodies distribute fat and muscle. The crew is also a small isolated population. That means inbreeding is a risk if you do not manage mating patterns and add genetic diversity from stored sperm, eggs or embryos. Even with careful planning, random genetic drift will push the group's genetics away from the original Earth population over time. After 100 years, you could measure clear differences in average stature, bone density, immune profiles, even in circadian rhythms tuned to the ship's artificial day-night lighting cycles instead of the 24-hour Earth day. On top of biology, there is psychology and culture. Hardware can be replaced, data can be backed up, but minds, stories and motivations are much harder to keep stable over 4 or 5 generations. What does it do to people to know that their entire world is metal walls, recycled air, and a mission goal they will never personally see completed? We have hints from submarines, remote research stations, and polar winter crews. Isolation changes people. It can drive depression, conflict, boredom, and groupthink. Small social problems that would be minor in a city of millions can become life-threatening in a closed community of a few hundred. Over decades, norms shift. New beliefs grow from the ship's daily reality, not from Earth's launch day speeches. The original mission, reach this star or survey this region, is a story told by one generation to the next. If that story is not kept active and convincing, if it does not adapt as circumstances change, it risks fading into background noise or myth, or something people pay lip service to while quietly caring more about local ship issues. By year 80, the mission patch and the founding documents might feel as distant to the crew as old national flags and ancient laws feel to us. So after 100 years, if humans are on board, they are not the same population that left. Their bodies have grown up under different gravity management, different radiation and different ecosystems. Their genes have drifted, their microbes have evolved, their language and culture have adapted to the reality of steel corridors and vacuum outside. They are still human, but they are shaped by the ship in deep ways. And that leads directly to the hardest technical challenge for a crewed century ship. Keeping people alive is not just about medicine. It is about keeping the entire environment around them stable, the air, the water, the food, the waste loops, for generation after generation. So the next question is, can you really run a closed life support system for 100 years straight, with no outside resupply, and not have it slowly slide toward failure? Keeping people alive for 100 years in a sealed ship comes down to one brutal fact: you are breathing, drinking and eating the same atoms over and over again. So the first question is, can you really recycle your air that hard for that long without running out? On the ISS, life support can recover around 90 to 95% of water and oxygen. That's good for a station that gets resupplied. For a century ship, that is not good enough. Over 100 years, losing even a few percent each cycle drains your original stockpile completely. You need closure much closer to 99.9% for oxygen and water, or you eventually hit a hard wall. CO2 scrubbers are the first line. You can use solid amines, metal oxides, or other sorbents that grab carbon dioxide from the air, then release it when heated so they can be reused. Or you use chemical reactors, like Sabatier systems, that turn CO2 and hydrogen into water and methane. That water can be split back into oxygen and hydrogen. All of this has to run not for months but for decades, with materials that can be regenerated again and again. Any leak in that loop is deadly in slow motion. If a little oxygen gets bound into plastics or trapped in long-lived organics, if a tiny fraction of water is permanently lost in filters, gaskets, or hard-to-recover waste, those losses add up. At year 10, it's a rounding error. At year 60, it's a crisis. So the system has to track atoms at a scary level of detail, and the crew has to treat oxygen the way a diver treats air at depth, as something that is always running down unless you fight for it. If the air loop is that tight, the water loop has to be even tighter, because water is everywhere in your life, not just in your lungs. So what does it look like when every drop of H2O on the ship is basically non-renewable? Current space stations already recycle water from breath, sweat, and even from equipment runoff. They use filters, distillation, and chemical treatments. Over a few years, those systems foul. Membranes clog with minerals and organics. Filters get loaded with biofilms. On Earth, you just swap cartridges and send the dirty ones to a landfill. On a Sentry ship, every filter you don't pack at launch is a filter you have to build out there, from the materials you have. So your life support hardware is not just a static set of machines. It's a full-time water treatment plant and a small chemical industry. You're constantly cleaning membranes, burning off organics, distilling small side streams to remove dissolved salts, and breaking down stubborn compounds. Microbial growth in water lines has to be controlled without wasting biocides. Scaling in pipes has to be prevented or removed without losing too much water in the process. The mindset becomes this is not used water, this is in the wrong place water. Condensation stuck behind a panel, moisture in a filter, even the water content of certain wastes is tracked. Over 100 years, you can't afford to write off even a small constant trickle. If you do, one day the tanks don't fill, the plants wilt, and the air system starves for hydrogen. Air and water can be recycled with machines, but food is different. You can't just store 100 years of meals in boxes for a whole crew. So how do you actually feed people for a century in a closed metal world? Dry rations are great for the first years, maybe even the first decade as backup. After that, you need bioregenerative systems, living agriculture. That means hydroponic or aeroponic plants, growing in nutrient solutions under LED lighting, maybe algae tanks, maybe insect farms for protein. Plants take in CO2 and water, give back oxygen and edible biomass. In theory, it closes the loop. In reality, you're running a complex farm in a very unnatural place. Crops can fail from disease, pests, or nutrient imbalances. A fungus that learns to exploit your main staple crop can threaten the whole food chain. Over decades, you learn which plant combinations stabilize, which become fragile. You fine-tune nutrient recipes, light cycles, and harvest schedules to keep yield steady. You also have to recycle every element in those food cycles. Nitrogen, phosphorus, potassium, trace metals, all of them have to come back out of waste and into fertilizers. If phosphorus starts quietly building up in some inaccessible reservoir, or if a trace element keeps getting locked into a waste stream you can't easily process, your crops eventually show deficiencies or toxicities. The farm is as much about chemistry and microbiology as it is about planting seeds. Once you start farming in a closed loop, you hit the next hard rule: nothing is really waste anymore. So what do you do with everything you would normally throw away, including things you really don't want to think about recycling? On Earth, you send trash to landfills, you flush toilets into treatment plants you never see, you bury hazardous waste and forget it. In a Sentry ship, that mindset will kill you. Every atom of carbon, nitrogen, phosphorus, and other key elements has to come back into the loop sooner or later. Feces and urine are not waste, they are nutrient packages. They get processed through bioreactors, composting systems, or advanced chemical plants to remove pathogens, stabilize compounds, and produce safe fertilizer or raw chemicals. Plastics that break or wear out become feedstock for recyclers, ground down and remade into new parts or burned in controlled ways to recover elements. Metals are melted, recast, and remachined. Even the most disturbing case, human bodies after death, have to be treated as part of the material cycle. Cremation or chemical breakdown can return water, carbon, nitrogen, and minerals to the system. Emotionally, that is hard. Thermodynamically, it is mandatory. On a 100-year Starship, Trachea is just the name for resources you have not figured out how to reuse yet, and entropy, the natural tendency for things to spread out and become unusable, is your real long-term enemy. If all this sounds like a tight balancing act, it is, and that brings up maybe the most dangerous part of closed-loop life support control. How do you keep all these interacting cycles stable for 100 years straight, when even simple ecosystems can flip suddenly into new, bad states? Closed ecosystems are not linear machines. They behave in messy, non-linear ways. Push one part a little too hard and another part swings unexpectedly. You might see algae blooms in water systems, killing fish or clogging filters. You might see CO2 spikes if plant productivity drops for a while. You might get nutrient crashes if some microbe suddenly dominates and locks up a key element. Sensors themselves drift over time, so a CO2 reading that was accurate at launch might be off by 10% after decade if you don't recalibrate it. Actuators age, valves stick, pumps weaken. Feedback loops that were stable in simulation can start to oscillate in real life, causing cycles of too much and too little as the system overshoots and corrects. So you don't just need fixed control software, you need AI systems that can relearn the ecosystem as it changes. They must notice new patterns, update models, and sometimes completely redesign control strategies. The life support system is less like a thermostat and more like a gardener, constantly adjusting, pruning and rebalancing with tools that themselves are aging and changing. Over 100 years, the ship's biosphere will not be the same as it was at launch. The mix of microbes, the crop choices, the nutrient pathways, even the average CO2 and O2 levels might shift within safe bounds. The trick is to stop those shifts from crossing invisible thresholds, where the system flips into a state you can't easily recover from, like a massive crop failure or a toxic microbe takeover. By the end of the first century, if you've succeeded, your life support is still running, but it's not the clean, simple loop drawn in the original design documents. It is a patched, adapted, partly evolved network of machines, tanks, pipes, microbes and crops, all balanced on the edge of stability. The crew is alive because that fragile balance is not tipped yet. And remember, all of this is happening while the ship is still ploughing through the interstellar medium itself, through gas and dust that are not entirely harmless at your speed. So the next question is, after 100 years of ramming through almost nothing at 1/10 the speed of light, what has that nothing really done to the outside of your ship and the space around it? After 100 years at 1/10 the speed of light, you're not just moving through empty black, you're ramming through a real medium, and even almost nothing starts to matter. So with densities of only about 1 atom per cubic centimetre, is the interstellar medium actually doing anything to your ship? Near the Sun, typical interstellar gas densities are roughly 0.1 to 1 hydrogen atom per cubic centimetre. That is a far better vacuum than any lab on Earth. It sounds like nothing, but your Starship is ploughing through that nothing at about 0.1 C, around 30,000 kilometers per second, about 19,000 miles per second. At that speed, each proton and tiny ion hitting your bow is carrying a lot of kinetic energy. The result is a weak but continuous erosion and heating effect on the forward-facing surfaces. Over seconds or minutes, it's trivial. Over years and decades, it is a steady sandblasting by atoms instead of grains of dust. The very front layers of your shields and armour see this constant particle wind, converting some fraction of the ship's huge kinetic energy into local heating and atomic-scale damage. It's not tearing chunks off, but it is constantly nudging the material away from its original state. And because you're moving so fast, the medium you're flying through does not stay spread out and quiet around you. It piles up, forming structures of its own. So what kind of weather does your ship create in the gas and plasma ahead of it? If your ship has any kind of strong magnetic field up front, or even just charged surfaces, it interacts with the incoming charged particles. Ions and electrons from the interstellar medium don't simply slam straight into the hull. Many of them get diverted, compressed or slowed by your fields. Ahead of the bow you form a tiny bow shock, a region where the gas gets denser, hotter, and more ionized as it's forced to flow around the ship. Around the hull, especially near charged or magnetized components, you build up a plasma sheath, a cloud of ionized gas and trapped particles. This sheath can be asymmetric, time variable, and messy. It bends particle trajectories, affects how fields from your own systems propagate, and can interfere with sensitive instruments that look forward along the direction of motion. Star trackers, radar, and radio antennas pointed upstream all have to deal with signals passing through a layer of disturbed plasma that your own motion is creating. This turns what's right in front of the ship into a full research problem, not just a minor detail. You need sensors and models just to understand the sheath you live in, because it affects both what you see outside and how your fields couple to the environment. Now, some Starship concepts try to use this gas, not just push through it. The classic idea is a Bussard ramjet, scooping interstellar hydrogen with big magnetic fields and using it as fusion fuel. After 100 years in real interstellar densities, how much gas do you actually collect? The honest answer is not much. At those typical densities, even if you sweep out a huge effective cross-section with magnetic fields, the mass you gather per second is tiny. At realistic field strengths and scoop sizes, you're talking grams to maybe kilograms of hydrogen collected over years, while your ship mass is hundreds or thousands of tons. Over 100 years, passive accretion might give you kilograms to tons of gas in total, which sounds like a lot until you spread it over the whole ship and mission. That is nowhere near enough to run a continuous high-thrust fusion drive. What it can be is a helpful bonus, extra mass you can use as reaction mass for small maneuvers, or as a coolant or feedstock for chemistry. But as a primary fuel source for big propulsion, the numbers just do not work out in your favour unless you push field strengths and collection areas into extreme speculative territory. Meanwhile, whether you scoop or not, you still have another effect to deal with. Moving a big charged object through a magnetized plasma is like dragging a conductor through a magnetic field. You generate currents and voltages. Over a century, that adds up to serious charging behavior on the hull. As you travel, different parts of the ship pick up charge at different rates. Some surfaces emit electrons, some collect ions, some are shadowed, some are sunlit by distant stars or your own power sources. The end result is that sections of your hull can charge to thousands of volts relative to the ambient plasma. When that potential difference gets too big, the system can suddenly discharge in sparks and arcs across surfaces or through the surrounding gas. Those discharges create electromagnetic noise, physical pitting, and potential upsets in nearby electronics. So you can't just let the hull float to whatever voltage physics wants. Active charge control becomes a standard, always-on subsystem. Electron guns, plasma contactors, and controlled emission surfaces quietly bleed off excess charge, keeping the whole structure within a safe potential range. It's like a slow-motion lightning protection system that has to work non-stop for 100 years. So over a century, gas is there everywhere, but in low density, doing gentle, widespread erosion and causing charging and plasma effects. Dust, which we talked about earlier, is rarer but far more violent. How do those two threats combine on your forward shields? Gas is the background. It hits all the time at every square millimetre of the bow. It gradually warms and erodes the first layers of material, atomic layer by atomic layer, leaving a thin, relatively even effect. Over 100 years, that might mean a shallow, worn layer, altered material properties, and a slightly receded surface. Dust is the sniper. Most of the time, nothing big hits. Then a grain comes in on a bad trajectory, at a bad relative speed, and blasts a microscopic crater, or worse. Each of those events is local, sharp, and potentially catastrophic if it strikes something vulnerable. Look at your forward shielding after a century, and you can read the difference. You'll see a uniform smoothing and modification of surfaces from gas, plus a random sprinkling of pits, cracks, and patched over damage from dust. Shield design has to survive both regimes at once. The bow can't just be a thin, delicate scoop or a fragile sail. It needs enough mass and layering to survive constant atom-level erosion and to take a few serious hits without failing. That's why realistic interstellar Starship concepts tend to look squat, armoured, and heavily shielded in the direction of travel, more like a blunt bullet or a flying bunker than a sleek science fiction yacht. At 0.1 C, the interstellar medium is not just a backdrop, it is an environment that is actively trying to strip, charge and crack anything you put in front of it, every second for 100 years. And all the while, tiny forces from this gas and dust, from photon pressure and venting and uneven heating, are constantly tugging on the ship, twisting it and feeding vibrations into its structure. So the next question is, after a century of these tiny random pushes and shakes, what has happened to your Starship spin, its resonances, and its overall structural health? Your Starship looks calm and steady from the inside, but over 100 years, it is always being pushed, twisted, and shaken by tiny forces. The question is, those tiny torques actually matter, or can you ignore them and trust the structure to stay still? Every time sunlight or starlight hits one side more than the other, photon pressure gives a tiny push. Every time a thruster fires a bit off center, or one nozzle is slightly weaker than its twin, you get a small imbalance. Any slow venting of gas, even from life support or a leaking line, pushes in one direction. In a week, these are noise. In a decade, they are a real change, a torque equivalent to the weight of a sheet of paper held at arm's length, applied constantly, is almost nothing in human terms. But apply that to a multi-ton structure for 10, 20, 50 years, and you can spin it up to degrees per hour of rotation. That is enough to mess with pointing, communications, and artificial gravity systems. So your control system is always fighting these drifts, using reaction wheels and tiny thruster firings to cancel unwanted rotation. But rotation is only part of the problem. The ship is not a rigid brick. It has natural frequencies, its own notes it vibrates at. So what happens when everyday operations keep poking those same frequencies, cycle after cycle for decades? Every structure, from a small antenna boom to the full length of the ship, has natural modes of vibration. Some are slow, maybe one full flex every few seconds. Others are fast, tens or hundreds of times per second. Thrusters firing in pulses, reaction wheels, spinning and adjusting, pumps, fans, even people walking in a rotating habitat, all inject vibrations into the frame. If one of those repeating disturbances lines up with a structural mode, you can slowly build up flexing in that part, even if each push is small. Over weeks or months, you might not notice. Over years and millions of cycles, microscopic cracks can start at welds, bolt holes, and sharp corners. That's fatigue, driven not just by temperature swings, but by mechanical resonance. To avoid this, engineers tune the ship. They try to keep operation frequencies away from the worst modes. They add damping where modes are strong. They monitor vibration with sensors, looking for certain patterns growing over time. But over 100 years, mass distribution changes, connections loosen, repairs alter stiffness. The natural frequencies drift, and something that was safe at launch can edge closer to a dangerous match decades later. This is even more critical if you're using a rotating ring for artificial gravity. That ring is both your home and a big spinning flywheel. So what happens to that ring if its mass stops being perfectly balanced over a human lifetime? A rotating habitat ring needs its mass distributed evenly around the spin axis. If one side is heavier, the ring wants to wobble and precess. In the short term, that shows up as slight changes in perceived gravity around the ring, small vibrations in the bearings, and weird loads on the supporting trusses. Over years, those extra loads add up. Bearings wear faster on certain sides. Trusses flex more in some regions than others, feeding fatigue. Over decades, people move equipment, shift storage, reconfigure living spaces, and add patchwork repairs. One sector might end up storing more spare parts. Another might hold more water tanks. That slowly increases imbalance. Left unchecked, a small offset can grow into a serious wobble. So long-term structural health monitoring of the ring is not optional. You need to weigh sectors, track changes in vibration patterns, and physically move mass around, like adding or removing counterweights to keep the system balanced. Mass balancing is not a one-time job, it's routine survival work. While all this is going on, the ship is constantly getting hit by micrometeoroids and dust. Each impact is tiny, but each one is also a little hammer blow. How does that constant pinging show up in your structure over a century? Every micro-impact launches a short, sharp stress wave through the local material. It's like tapping a bell with a tiny hammer. One hit does nothing. Thousands and millions, spread across many years, become a form of random vibration input. Thin panels, radiator pipes, sensor booms, and delicate supports are especially vulnerable. These components are like small tuning forks. A certain distribution of impacts might by chance keep hitting a mode they respond to strongly. Over time, repeated flexing, even at microscopic levels, can start cracks, especially when combined with thermal and radiation damage. Sensors on the hull will record a background of these hits as little spikes. For the structural health system, those spikes are not just noise, they are data you use to estimate how much fatigue each area is accumulating. To push back against all this, some advanced Starship designs use materials that do not just passively take damage, they react to it. So what happens if your structure can partially heal itself, and how does that change over 100 years? Shape memory alloys can change shape when heated and return to a preset form, helping close small gaps or restore alignment after minor distortions. Crack-arresting composites can stop small cracks from growing by diverting them into harmless directions. Self-healing polymers can carry microcapsules of resin that burst when a crack forms, filling and sealing it before it spreads. At the start of the mission, these adaptive materials give you a lot of extra safety. Micro cracks that might have grown into failures instead get blunted or filled. Alignment errors from small deformations can be corrected with controlled heating cycles. The ship behaves tougher and more forgiving than a purely passive structure, but these systems draw down internal reserves. Every time a self-healing polymer releases resin, it uses up some of its limited supply. Every time you cycle a shape memory alloy to reset a part, you add a bit more fatigue. Over 100 years, you can exhaust the healing capacity in certain areas. A beam that could self-seal many times in the first decade might only be able to do it once or twice in the last decade, or not at all. That means the mechanical personality of the ship changes with age. Early on, it shrugs off minor damage. Late in life, the same level of stress leaves permanent scars. Engineers have to design not just for how stiff and strong the structure is at launch, but how that stiffness and strength will evolve as self-healing systems go from fresh to depleted. Monitoring systems have to track how much healing budget is left, so you do not assume you have safety margin that is already spent. By the time you hit the 100-year mark, your Starship has been slowly spun, shaken, pinged, and partially healed for a very long time. Its spin state has been fought and corrected thousands of times. Its resonances have drifted, its ring habitats have been rebalanced again and again. The frame still holds, but it is no longer the same clean structure that left Earth. It is a used, adapted, slightly warped machine that remembers every tiny push it ever took. And all of this, every correction, every pump, every sensor, every heater you've used to keep the structure stable, runs on power that is also fading and aging. So the next question is, after 100 years at the edge of interstellar space, what does your energy situation really look like? When your solar arrays are useless, your RTGs are fading and your batteries are older than any on Earth? After 100 years in deep space, the biggest quiet change is this. The power you launched with is not the power you have now, so start with the most obvious source, solar panels. Do they still matter when you're light years away from the sun? Near Earth, at 1 astronomical unit, sunlight gives you about 1,360 watts per square meter. That's plenty for big solar arrays. Move out to 10 astronomical units, roughly Saturn's orbit, and that drops to about 13.6 watts per square meter, 100 times less. Push beyond 100 astronomical units far outside the heliosphere, and the flux from the sun is so low that your huge array is basically dead weight. Unless your trajectory keeps you close to a star for most of the mission, your solar panels do almost nothing after the first few decades. They still take micrometeoroid hits, They still get darkened by the radiation and coated with tiny impact craters. Their big surface area adds more target for dust and helps torque the ship under photon pressure, but in deep interstellar space they provide almost no useful power. At that point they're more shield and drag than generator. So you stop relying on sunlight and fall back on nuclear sources. The first, simplest nuclear power option is the RTG, the radioisotope thermoelectric generator. Those are the always-on hearts of many deep space probes. What do they look like after 100 years? A typical RTG fuel, plutonium-238, has a half-life of about 88 years. That means in roughly that time its heat output drops to about half. Add another decade or so and you're down to roughly 40 to 50% of the thermal energy you started with. On top of that, the thermoelectric devices that convert heat to electricity also degrade. Their temperature gradients shrink, their efficiency falls. By the end of a century, your RTGs might be giving you only about a third of the electrical power you had at launch, sometimes less. Early in the mission, you could run instruments, heaters, comms, and computers with margin. Later, you have to schedule everything. High-power instruments may only wake up once in a while, maybe a few hours or days per year during carefully planned campaigns, while everything non-essential shuts down to free up power. If you have a small fission reactor instead of, or in addition to, RTGs, the situation is more complicated. On paper, a reactor can run for decades. In practice, long-term operation depends on moving parts and chemistry that do not like being ignored for 100 years. Reactor systems have pumps, valves, control rods, heat exchangers, and coolant loops. Materials in and around the core embrittle from radiation. Coolant chemistry slowly changes, picking up corrosion products and fission fragments. On Earth, teams of humans constantly monitor and maintain all this. On a Starship, you don't have that luxury. So for 100-year missions, a fission reactor is usually either used in a short, intense period, then shut down permanently, or is run at very low power and low-duty cycle, stretching out its life by keeping mechanical and thermal stress minimal. You might run the reactor hard early on to power big propulsion burns and heavy science, then transition to RTGs and a quiet, low-power mode for the long cruise. You generally do not plan on firing a high-power reactor up and down for many decades without hands-on maintenance. No matter where the power comes from, you need ways to store it and deliver it in bursts. That's where batteries and other storage systems come in, and here again, 100 years is far longer than most chemistries can handle. Lithium-ion batteries, the kind you see everywhere today, lose capacity over hundreds or a few thousand cycles, and they age even when just sitting there. Electrolytes break down, electrodes grow unwanted structures, seals slowly degrade. Over a century, normal Li-ion packs are basically consumables, not permanent infrastructure. You can't count on a chemical battery built on Earth and launched on day one to be healthy in year 80 just because you barely used it. For long-duration storage, you may shift to systems that either have very low chemical reactivity or are purely mechanical or electromagnetic. Supercapacitors can handle many more cycles, but store less energy per kilogram. Flywheels can store energy as rotational motion in heavy spinning masses, but they put stress on bearings and need containment in case of failure. In many cases, the safest long-term strategy is to minimize reliance on large dedicated storage and instead design the ship to use RTG or reactor power directly as much as possible, flattening loads instead of repeatedly charging and discharging big batteries. By the time a century has passed, all of this adds up to one reality: the ship has to learn to live with less power every decade, while its systems get hungrier for maintenance. So how does it actually manage that trade over time? Early in the mission, when RTGs are strong or reactors are fresh, you can run a wide suite of instruments, heaters, backups, and luxuries. You can keep multiple communication paths hot, operate redundant sensors, and run detailed self-diagnostics frequently. Power budgets have margin. As sources fade and components age, you start cutting. Non-critical experiments are powered down permanently. Some instruments are run only rarely, when geometry is perfect or when a high-value target is in view. Internal temperatures might be allowed to drift a bit wider, relaxing heater usage at the cost of more thermal stress on hardware. Data processing moves toward more on-the-fly filtering, so you don't need as much power for storage and transmission. Mission control back home, if it still exists, will send updated priorities. Onboard AI will adjust too, sometimes choosing to abandon older experiments so that core navigation, health monitoring, and a few high-impact scientific campaigns can continue. By year 100, the ship that launched ready to study everything has become very selective. It's like an old scientist with limited energy, picking only a few key observations to make before it finally goes dark. And with power this tight, one more thing becomes dangerous. Any waste you spend on constantly correcting your path and pointing. Navigation, attitude control, and communications geometry all cost power, directly or indirectly. So the next question is, after a century of drift, sensor aging, and sky changes, how well do you actually know where you are, and how much do you have to spend just to keep your antennas and instruments pointed at the right targets? After 100 years in deep space, the scariest failure isn't a broken engine or a cracked panel. It's this. You might simply stop knowing exactly where you are and where you're pointing. So start with your main eyes on the sky, the star trackers. How do they hold up when the sky itself is shifting under you? Star trackers work by taking pictures of the stars, then comparing what they see to an onboard catalogue. At launch, that catalogue matches the universe very well. But stars have proper motion, they drift across the sky slowly, and your instruments themselves age, their optics darken, their sensors change sensitivity. Over 100 years, some bright nearby stars move enough that the angles between them and their neighbours are clearly different from launch values, if you look with precise instruments. If you never update your catalogue, the tracker starts to get confused. It sees patterns that almost match, but not quite, and the software begins to misidentify stars. That leads to attitude errors. At first, they're tiny. Then you're off by arc minutes. Then more. Your high-gain antenna might miss more Earth. Your telescopes might point slightly away from a target. Your navigation burns might go in the wrong direction. The fix is obvious but demanding. You must let the ship rebuild its own catalogue. Over time, the star tracker doesn't just match against a frozen list. It measures positions again and again, uses parallax from the ship's motion to update distances, and feeds that into an internal model of the local stellar neighbourhood. It effectively becomes its own small observatory, updating its map of the sky so it can still trust star patterns after a century of motion. But even with perfect star tracking, you also depend on something else. Your sense of rotation from inertial systems, gyros. These don't watch the sky, they watch your own turning. What happens when the devices that feel your spin slowly forget the truth? Ring laser gyros and fiber optic gyros are very stable, but not perfect. They drift, even when carefully temperature controlled. On short missions, regular star tracker updates reset that drift before it matters. Over years and decades, especially if some sensors start to fail or get noisy, the picture gets messy. Maybe one axis of a gyro unit becomes noisy but still partly useful. Maybe another axis dies completely. Radiation adds random spikes. Thermal cycles change alignment. You end up with a patchwork, some data good, some bad, all of it needing constant cross-checking. By 100 years, a lot of your original inertial measurement units are degraded. Navigation shifts to lean less on them and more on external references, like stars and pulsars. The IMUs become short-term smoothing tools, not long-term truth sources. Your onboard navigation AI spends a lot of effort weighing which sensors to trust at any given moment, instead of just taking gyro readings at face value. And even if your attitude is perfect, your position is not just a simple straight line from launch. Gravity and tiny forces have been nudging you the entire way. So how far has your actual path drifted from your original perfect trajectory? As you pass within light years of stars, star clusters, or denser regions like molecular clouds, their gravity tugs on you just a little. Over a few years, that might change your velocity by fractions of a meter per second, which feels like nothing. Over decades and light years, those tiny changes add up. your trajectory bends in ways that your original flight plan didn't fully predict. On top of that, you have asymmetric outgassing, tiny leaks pushing gently in random directions. Dust impacts that transfer a little bit of momentum. Photon pressure that is not perfectly balanced. Each effect is small, but they all push you off the ideal line. After 100 years, your true path is not a razor-thin track. It's a probability cloud, a region of space where you most likely are, with error bars that grow with time, unless you constantly correct and measure. To pin down your place more accurately, you look for something more stable than drifting constellations, and that's where pulsars come in. Can they really act like a kind of galactic GPS for your century ship? Millisecond pulsars spin extremely fast and regularly, sending out pulses of radio or X-ray beams with periods that can rival atomic clocks in stability. If you have good receivers and a model of where those pulsars are and how their signals travel through the galaxy, you can time their pulses and triangulate your own position. By observing several pulsars from different directions, measuring the precise arrival times of their pulses, and comparing those to predicted times, your ship can solve for its location and velocity, often down to tens of kilometers or better, even across huge distances. That's far from perfect in everyday terms, but incredibly precise at interstellar scales. However, this only works if you keep your pulsar ephemerides, your tables of pulsar positions and timing behavior, up to date. Pulsars can glitch, suddenly changing their rotation rates a bit. They slow down very gradually over time. Interstellar plasma can also delay their signals. Your navigation system has to model all that, update it as new data comes in, and notice when a pulsar you trusted has shifted a behavior enough that your old model is wrong. So you're constantly juggling star trackers, degraded gyros and pulsar timing just to know where you are and how you're pointing. Then you want to talk to home, but home has been moving too. How do you keep a tight communication beam locked on a target that's been orbiting and orbiting while you've flown for a century? Earth is not fixed. It orbits the Sun once a year. The Sun orbits the center of the Milky Way once every 200+ million years. Your home system slowly bobs up and down through the galactic plane, while nearby stars tug on its path. After 100 years, the vector that would have pointed to Earth at launch is completely wrong. When you send a signal, it does not arrive instantly. Depending on distance, it could take years to reach the receiver. So the ship has to solve a 4-dimensional geometry problem every time it wants to talk. Where is the receiver now? Where will it be when the signal gets there? And how do I aim my narrow beam so that it crosses that future point? Narrow beams are necessary because you have limited power and huge distances, but at light-year scales, even a pointing error of a few microradians, a fraction of a degree, can mean your beam misses the target by millions of kilometers. With degraded attitude sensors, changing star fields, and uncertain exact positions, keeping that lock becomes harder as time goes on. By year 100, navigation is less about following a pre-planned perfect path, and more about constantly updating a best-guess state based on aging instruments and external cosmic lighthouses, then squeezing every bit of accuracy you can out of dwindling power and fading sensors just to stay in touch. And if just figuring out where am I and which way am I facing is that hard, there's an even darker question behind it. What has happened in those 100 years to all the information you're carrying, the data, the culture, the instructions, the meaning of the mission itself? How much of what you left with is still intact, and how much has quietly rotted away inside your storage systems and your own evolving society? After 100 years, the ship's metal is scarred and the engines are tired, but there's a quieter question that might be even worse. How much of what you know is still there, and how much has already slipped away without anyone noticing? Start with the hardware that holds your data, the storage. We like to think of bits as permanent, but no real storage medium is built for a clean 100-year ride through deep space. Magnetic tapes lose magnetization. Optical discs get micro cracks, layer separation, and radiation damage. Flash memory cells leak charge and suffer from cumulative write wear. Even if you baby them with stable temperatures and shielding, none of these media are guaranteed to stay healthy for a century under constant radiation and occasional power glitches. bit error rates slowly rise, bad sectors appear, and whole devices can quietly degrade. That means you cannot treat any storage as write once, say forever. The only workable strategy is continuous migration. The ship has to periodically read everything it cares about, verify it with checksums and error-correcting codes, and rewrite it onto fresh blocks across multiple devices and different media types. Important data exists in several copies in different places and gets rotated over time like crops in a field. If you fall behind on this, if power is too tight or systems get busy and you skip migrations, some data will rot. First a few bits, then whole files, then entire volumes. By the time errors show up in day-to-day use, you've probably already lost more in the background. Even if you keep the bits electrically correct, there's another way information can decay, every time you transform it. What happens when you keep compressing, converting, and resaving data across 100 years of software updates? Every time you recompress an image, an audio stream, or even some logs, you risk losing detail. Lossy formats throw away unnecessary information to save space. Do that once, fine. Do it over and over. Across generations of codecs and tools, and subtle details vanish. Lossless formats help, but they depend on software that knows how to interpret them. Metadata standards change. File formats evolve, parsers get rewritten, and sometimes simplified. A science instrument in Year 5 might store data in one custom binary format, with a certain header structure and unit conventions. In Year 70, newer tools might still be able to read the bits, but no one has used that path in decades. A minor bug in a converter, or a missing piece of documentation, can make the data effectively unreadable. After a century, you can easily end up with archives that are intact at the bit level, but semantically dead. The ship has the bits, but not the working stack of software, documentation, and context needed to make sense of them. It's like having a library of books in a language nobody on board can read anymore. While all this is happening, the ship itself is making choices about what to keep active. The mission started with clear goals: map this, reach that, send back these measurements. But after 100 years of failures, power cuts, and onboard optimization, do those original goals still dominate what the ship actually preserves? The control AI and crew have to prioritize survival first. When storage runs low or power is tight, they trim. High-risk experiments get shut down. Redundant logs get shortened. Old calibration files that haven't been needed in years get archived to slower, less reliable media, or deleted outright. Cultural archives that don't seem mission-critical can get pushed aside to make space for fresh navigation data, health logs, or updated software. Over time, what stays visible and robust is what gets used, checked, and refreshed often. Navigation software, current sensor drivers, current language, current procedures. What quietly fades is what no one touches. Old art files, old educational materials, obscure languages, niche scientific datasets. Entire slices of humanity's history and culture can vanish from primary storage simply because for 60 years, no one on the ship had a direct, urgent reason to open them. Even if the bits survive and are readable, there's another drift you have to worry about: language and codes. If humans or AIs on board are still talking, writing, and programming after 100 years, are they still speaking in a way Earth can understand? Language is not static. Slang emerges, meaning shift, grammar changes. Technical jargon evolves as systems are repaired, repurposed, or replaced. A message sent home in year 90 might use abbreviations, references, and field names that made perfect sense on the ship but look strange to analysts back on Earth, whose own language and standards have also shifted. Protocols change too. Cryptography that was considered unbreakable at launch might be trivial by year 100 on Earth. People on the ship might adjust their encryption, compression, or packaging methods based on their own needs, not realizing that old decryption keys, old libraries, or old documentation on Earth have been retired or lost. You could end up in a situation where both sides are receiving packets, both have the raw bits, but neither can fully decode the other's content without huge effort. The information crossed the gap physically, but mutual intelligibility decayed. The only real defense against all this is to treat redundancy and context as part of the payload, not an afterthought. So what does it look like when you design your data with "don't forget how to read this" as a core requirement? You don't just back up files, you back up understanding. That means storing multiple copies of data in different formats, some compressed and efficient, others simple and bulky but easy to parse. It means keeping old compilers, old interpreters, and full virtual machines that can emulate the original environments your software ran in. It means shipping human-readable specs that explain file formats, units, coordinate systems, and assumptions in plain language, not just code. Onboard AI systems periodically test that old stacks can still run, that old data can still be opened and interpreted end-to-end. If they find a broken link in that chain, they try to repair it while enough context still exists. You also assume that your own way of thinking might die. So you package multiple independent ladders to understanding, different languages, different explanatory styles, maybe even visual and symbolic aids that don't depend on a specific cultural background. The goal is that if one civilization, either on the ship or on Earth, loses its tools or changes too much, another still has enough redundancy to climb back up and resurrect the meaning hidden in those bits. By the 100-year mark, whatever knowledge and culture still live on the Starship have survived not just hardware damage and radiation, but also forgetfulness, drift, and shifting priorities. What's left is a filtered subset of what humanity once sent, shaped by what was useful, what was maintained, and what was lucky enough to be continually reread and re-explained. And that sets up the final question. When you look at this 100-year-old machine from the outside, as an artifact crossing the galaxy, what does it actually look like to the universe? What story does its scarred hull, fading power, and mutated data tell to anyone who finds it, including the descendants of the people who launched it? After everything you've heard, here's the weird part. A 100-year-old Starship is both insanely old and basically brand new at the same time. From a human point of view, 100 years is huge. Entire generations have been born and died since launch. The tech on board is a museum piece compared to what Earth has by then. The hull is pitted, the paint is gone, the radiators are scarred, the software has been patched and repatched so many times it barely resembles the original codebase. The RTGs are weak, batteries are tired, backup systems have been cannibalized. But on a galactic timeline, you've barely taken a single step. Crossing even a modest gap of 10 light-years at 0.1 c takes about a century. Crossing hundreds of light-years takes thousands of years. So after 100 years, the ship isn't at the end of anything. It is in the very first percent of its possible interstellar journey. All the damage, all the aging you've heard about is just the opening phase of deep time pushing back against human engineering. The ship is turning into a fossil, but in slow motion, while it still technically works. That raises the next question. Out in that dark, with fading power and a scarred hull, is your ship still something anyone else could actually find, or does it just vanish into the background? As the RTGs fade and any reactors are shut down, the radio beacons get weaker. What started as strong, sharp signals becomes tens of watts, maybe less, being tightly beamed in carefully scheduled windows. At distances of light years, even a focused beam like that is incredibly faint. Unless a receiver is exactly where it's aimed, at the right time, and knows what to look for, it's easy to miss. But the ship doesn't disappear physically. It still has mass. It still reflects and emits radiation. In radar or in very sensitive reflected light, it's a solid, geometric object, nothing like a natural asteroid. In thermal infrared, even a cold starship glows a little. Waste heat from electronics and decaying nuclear fuel leaking out as long-wavelength radiation. Its spectrum shows sharp edges, flat panels, repeating structures, and material signatures that don't match rock, ice, or dust. To an advanced civilization scanning the sky with serious instruments, A kilometers-long straight-edged object, running colder than a comet but warmer than deep space, would stand out. It wouldn't shout, but it would not look natural either. Even with little power left, the ship is still a detectable artificial artifact drifting between stars. If anyone ever gets close enough to study it directly, the hull itself is a record. So what exactly could someone learn just by scraping its surface and reading its atoms? Every dust grain, every gas ion, every cosmic ray that has hit the ship has left tiny traces. Ions of different elements get implanted a few nanometers deep. High-energy interactions can create rare isotopes or subtle changes in existing ones. Regions exposed inside the heliosphere early in the mission have a different radiation and particle history from regions exposed later in pure interstellar space. A future probe, or even humans arriving centuries later, could sample different parts of the hull and read the sat history like tree rings. They could see when the ship left the sun's protective bubble, how intense the cosmic rays were over time, maybe even distinguish between denser and thinner patches of interstellar gas the ship passed through. Your Starship has effectively been acting as a giant cosmic dosimeter for 100 years, storing a log of the radiation and particle environment in its own materials. For Earth, if it's still around and still listening, the ship is also a time machine in another sense. Every signal it sends home, every data dump, every health report is a message from the civilization that built it, not from the one receiving it. By year 100, the people on Earth who launched the mission are long dead. Their design choices, coding habits, and cultural references are frozen in the ship's hardware and software. You see it in variable names, in comments inside code, in the way subsystems are labelled, in the jokes embedded in test messages, in the choice of what music and books they included in the cultural archive. For the descendants on Earth, that material is a snapshot of who their ancestors were, what they feared, what they cared about, what they thought good engineering meant. Even if the mission is technically still ongoing, the ship itself has turned into an archaeological artifact, a living fossil that tells you how people thought about the cosmos a century earlier. Every time a weak ping comes in from that old hull, it's not just telemetry, it's a reminder of a different era of humanity. And here's the hardest part to swallow: if you've managed to keep a Starship alive for 100 years, you haven't solved the interstellar problem, you've solved the easy part of it. The jump from a 10-year mission to a 100-year mission is massive. You had to change how you design materials, software, life support, navigation, everything. But the jump from 100 years to 1,000 or 10,000 is on a completely different scale. All the processes that have been quietly eating your ship, radiation damage, thermal cycling, creep, information loss, cultural drift, just keep going. Cracks don't stop growing, bits don't stop flipping, power doesn't stop fading, languages don't stop changing. At 1,000 years, you are not just updating old hardware and patching old software. You are dealing with layers of repair on top of repair, cultures that have reinvented themselves multiple times, and materials that may have gone through several cycles of self-healing and partial failure. At 10,000 years, the original design intent is basically mythology. The Starship has become its own ecosystem with its own long-term evolution. At that point, a Starship isn't just a piece of engineering. It's a long bet against entropy, a test of whether intelligence can keep a complex, fragile structure functional across timescales where everything from atoms to ideas wants to drift, crack, or fade away. After 100 years in deep space, your ship is still moving, still working, still sending data, but it is also already something else. A damaged, adapted, half-fossilized machine carrying traces of a species that decided to step off its world and see how far into the dark it could push a fragile bubble of order. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.